want to welcome you all. This is our fifth speaker in a webinar series on transportation system resilience, extreme weather, and climate change. I'm Bob Johns. I'm director of the Volpe National Transportation Systems Center. We want to welcome all of you here in Cambridge who are going to listen to Dr. Emanuel. But I really want to welcome all of you who are on the web that are linked in. We have federal colleagues, state, regional, and local transportation organizations, universities, nonprofits, industry representatives, and international transportation participation. And we just learned that we have over 200 organizations signed up to hear this speech, over 25 states, and we even have the Civil Aviation Authority of Fiji. So we want to welcome all of you. At the end of the talk, we'll have time for Q&A, and we encourage those of you on the webinar to type in your questions, and we'll take those as well as those here in the audience. So it's my pleasure to introduce today's guest, Dr. Kerry Emanuel, who is the Cecil and Ida Green Professor of Atmospheric Science at the Massachusetts Institute of Technology. He's been on the faculty at MIT since 1981 after spending 3 years on the faculty of UCLA. His research interests focus on tropical meteorology and climate with a specialty in hurricane physics. His interests also include cumulus convection and advanced methods of sampling the atmosphere in the aid of numerical weather prediction. He's the author or co-author of over 100 peer-reviewed scientific papers and also 2 books, The Divine Wind, The History and Science of Hurricanes, published by Oxford University Press and aimed at a general audience, and What We Know About Climate Change, published by MIT Press. He served as professor and director of the program in atmospheres, oceans, and climate in the Department of Earth, Atmospheric, and Planetary Sciences at MIT from July 2009 to January 2012. He was elected to the National Academy of Sciences and serves on the Board of Atmospheric Sciences and Climate of the National Academy. He also served on the board of the University Corporation for Atmospheric Research and the Council of American Meteorological Society. Please join me in welcoming Dr. Kerry Emanuel.
Well, thank you very much, Bob. I'd also like to thank Ellen for being such a gracious host to me here. It's very nice to be with you here today to talk about climate and extreme weather. So what I'm going to start off doing today is just a brief overview of climate change. I'm sure you've heard a lot about the subject, and I'll just sort of give it a glancing blow here and then talk about what we know and also what we don't know about the relationship between climate and extreme weather. The heart of the problem, I think, is best illustrated by this little pie chart, which shows the composition of our atmosphere. As you're probably aware, almost all of the atmosphere is made of molecular nitrogen and oxygen. Oxygen's about 21%, nitrogen's about 78%. And then there's an inert gas, argon, which is almost 1%. And the rest of it is made out of water vapor, carbon dioxide, and other greenhouse gases. That's the orange sliver. Can you all see that orange sliver? No, probably not. That's the remarkable thing and a very deeply non-intuitive thing about our atmosphere is that, and this has been recognized for well over 100 years, is that the surface temperature of the planet is 15 degrees C on the average as opposed to minus 18 degrees C because of the existence of that orange sliver. All right? This is a great discovery, and it was quite shocking to the scientists who discovered it well more than 100 years ago, that our greenhouse effect depends upon a very tiny fraction of gases in our planet. So the difference between minus 18 degrees C, a frozen snowball, and our habitable planet is made possible by that little sliver. The problem is that we are increasing the concentration of the most important of the long-lived greenhouse gases, carbon dioxide. Water vapor is actually more important, but it responds very quickly to changes in temperature. We don't really control water vapor, and it's considered a feedback effect in the climate rather than a forcing. on timescales of hundreds of years. So this goes back about 2,000 years, and you can see that carbon dioxide concentrations were pretty stable around 280 parts per million, going all the way back to near the end of the last ice age. But beginning at the dawn of the industrial era, they've started to increase much more rapidly with time. And in fact, this year, they're exceeding 400 parts per million. So they're well on track to double or even triple, perhaps more. And that's the source of the concern. Now, there is a relationship between carbon dioxide and climate, which is shown fairly crudely in this graph, which shows the natural logarithm of the CO2 content. We think on theoretical grounds that surface temperature should be proportional roughly to that logarithm. And the global mean surface temperature itself, shown in green. There's chaotic and other variability of the temperature caused by just internal variability and other climate forcing agents like volcanoes, but by and large, the temperature has followed up the CO2 curve. There's not any real dispute in my field about this connection between carbon dioxide and climate. Where is the excess energy actually going? This is sort of shown by this chart, which is not of temperature, but of the actual energy content of the various components of the climate system. This blue part, which starts, this graph goes back to about 1965, up to more or less the present. All this blue part is the ocean, and the red wedge you see is everything else, the land ice, and the atmosphere. So by far the majority of heat, as predicted theoretically, goes into the oceans, not into the atmosphere. Exchange of heat between the atmosphere and ocean is an important part of the internal variability of the climate system. This is what happens more or less when we have El Nino, for example. Now, one of the sort of myths about our field, which I want to try to dispel for you in just a few minutes, is the idea that everything that we know about the climate is based upon enormous, complicated supercomputer models. Well, I'm not a big, complicated supercomputer model guy. I try to stay away from that stuff. These things are valuable tools, but you need to understand that our understanding of climate rests upon a whole lot more than that. So we can turn the clock back to the early, very early 20th century, actually the end of the 19th century, when this Swedish chemist, Nobel Prize-winning chemist von Arrhenius, looked at measurements of the passage of infrared radiation from the moon to the Earth. It was a great measurement program. Go out on nights when the moon was full and measure it, okay? And with nothing more than a pencil and paper, of course there weren't any computers in that day, he was the first to make an estimate or to start to worry about the fact that we were going to change the composition of the atmosphere and that would change the climate. So he wrote in 1906 that a doubling of carbon dioxide concentration would raise the surface temperature by about 4 degrees centigrade. And you can compare that to the most recent estimates by that August body, the IPCC, in their latest released report from last fall, saying that the surface temperature, if you double carbon dioxide, would go up somewhere between 1.5 and 4.5 degrees C. So not bad, Svante. You know, this is 100 years ago. No computers, just basic physics, right? You don't need supercomputers to tell you that there ought to be a response of that order. So the latest estimate from the IPCC, 1.5 to 4.5 degrees. Now, we can devise much simpler models. Here's one that we run at MIT. This is the kind of model you could run on your laptop. It's not a supercomputer model. And we've done all kinds of different experiments with these models. What you see on this graph is the number of doublings of carbon dioxide. Theoretically, temperature should go up more or less linearly with that measure. And so this is surface temperature, and these are just experiments, and the straight line fit to that gives about 3 degrees of warming for a doubling right in the middle of the IPCC range. So what we understand about the global response to carbon dioxide is more than 100 years old and not principally based upon big, complicated models. But we do use the best models that we can get our hands on to make projections, fully aware that they're uncertain. And there are lots of different sources of uncertainty, which I wanted to briefly touch on here. What you see here is from the most recent IPCC report released last fall. It's a projection out to the beginning of the next century. And on this graph is the radiative forcing change due to changing greenhouse gas concentrations and feedbacks associated with them. But this, in fact, excludes the feedbacks. It's just the direct radiative forcing. And these different curves are for different projections that basically have to do with what we do. Are we going to stop emissions? Are we going to slow them down? Are we just going to continue with business? Nobody can predict human behavior, so we have to rely on a bunch of different kinds of estimates. This blue curve is kind of a business as usual curve where we don't really do anything at all. And the radiative forcing change due to changing greenhouse gases goes up to about 8 watts or 8.5 watts per meter squared at the end of the century. But there are other projections that rely on estimates of human behavior, basically, what we might do to try to stop that. And when we look at a whole suite of global climate models run by different groups in different countries, we see that the projections entail a great deal of uncertainty. So this is where we're at now in the year 2014. This goes back to 1950 and forwards to the end of the century. And this is sort of the envelope of possible outcomes. And it's very, very broad, but it consists of the sum of a lot of different uncertainties. The uncertainty in emissions that I just showed you is given by the green. So if we go business as usual, we're going to go up much higher in temperature than if we try to curtail emissions. But there's also spread due to uncertainty in how to model the climate, given by blue, and just plain random or chaotic internal variability of the climate, the kind of variability that would exist if we weren't changing the forcing, given by orange. So this is the problem when you try to go to the future, is that there are multiple sources of uncertainty. There are no climate scientists out there who will tell you that we're completely certain about what's going to happen in the future. There's a whole lot of uncertainty. And how do you make decisions in the face of uncertainty? The same way you do with any sort of risk problem. You begin with a probability distribution of the event risk itself. So what you see here is a graph that was made by running literally thousands of different climate models on computers that were volunteered to this effort by ordinary people. You know, they said, yes, you can come in on the internet and run your model on my machine when I'm not using it. It's called Climate at Home. And the different models made all kinds of different assumptions. And this is sort of our best shot at the global mean surface temperature change you would get from doubling CO2. Now, you have to be very careful because we're on track to do much more than double CO2, but this is for a doubling. So the most probable outcome has a temperature change by the end of the century. It would be on the order of just shy of 3 degrees. And there's some possibility of a much smaller change. There's a 5% probability that the change will be less than 1.8 degrees, and a 5% probability that it will be more than 4.5 or so degrees. And when you assess risk, of course, you have to convolve this distribution with some estimate of how expensive to you, to your livelihood economically, or to your life socially, the outcome will be. And that curve is not well estimated, but it's terrifically nonlinear. In other words, the consequences of climate change in this region are probably not very serious. It's something we can probably adapt to. But if we go out here to 4 degrees or more, the consequences can be devastating. And when you get out into this tail, they might even be existential challenges so this is the problem, okay, that we face, is that there is a very risky tail to this distribution, a very expensive, risky tail. And so the problem for society is, how do you want to deal with that sort of risk? Now, as I mentioned before, depending upon which projection you want to follow, business as usual or something else, carbon dioxide concentrations, even in this century, will probably much more than double. So we start at the pre-industrial value of 280, and we're going up. This is where we are now. These are the various different emissions scenarios. And this light blue dashed line is the value you have from doubling pre-industrial CO2. So if we don't do anything at all, we're going to cross that line before mid-century. And by the end of the century, we'll have more than tripled the carbon dioxide concentration in the atmosphere. That tripling really is going into very, very risky territory. Everyone that I talk to believes that. We're taking a real gamble with future generations if we go down that road. The other problem with this is that you can't, for scientific reasons, afford to wait very much. And the reason that you can't afford to wait is that once you put carbon in the atmosphere, it takes a long time for it to go away. And that's shown by this graph at the top. This is both the history and a projection of carbon dioxide concentration in the atmosphere going back to 1800 and forward to the year 3000. And what's assumed here, for the purposes of making this graph, is that when the concentration gets to 450 or 550 or 650, we're just going to completely turn off emissions. It's very unrealistic, but it shows something that needs to be said. Once you shut off emissions, there's an initial fast decay of CO2, but it literally takes thousands and thousands of years for it to go back to normal. All right, and CO2 has a very long life in the atmosphere. If we go up to 850 or 1,200 parts per million, we're stuck with that value for thousands and thousands of years. It doesn't just go back to normal in a few years. If it did, we could afford to wait. This is a corresponding projection of global mean surface temperature that corresponds to this graph. So you can see that it takes many, many thousands of years for the climate to go back to normal once you stop putting carbon dioxide into the atmosphere. So when it comes down to, we're going to now transition to a discussion of extreme weather. When it comes down to human or societal consequences of global warming, a lot of these occur in the tails of distributions. You can think of this as being temperature or rainfall, whatever you like. If we have some sort of probability distribution in the current climate, what global climate change can do is, in this upper case, to shift the distribution, say, to higher temperatures. And where you see the big changes when you do this are in the tails of the distribution. So you start seeing temperatures you never saw before. And the really hot temperatures occur much more frequently. Conversely, the really cold temperatures occur far less frequently. Another thing that climate change can conceivably do is change the width of these distributions. That will also change the incidence of events in the tails. And of course, you can do both. So we have to account for this when we think about changes in extreme events. So if we talk about just plain heat, there's a certain mortality globally from heat waves. And what you see on this graph is, in black, a record of the Earth's mean surface temperature, again, going back to 1900. And in red, both the hindcast and the forward projection by a particular climate model. And just for comparison, this blue line here was the sort of Earth's mean surface temperature at the time of the big heat wave that killed 60,000 people in Europe in 2003. And the point is that that kind of heat becomes much more common as you go forward in time. You should not, on the other hand, take away from this the message that we're going to have these killer heat waves more and more frequently, simply because people adapt to heat up to a point. And that, I'll get to that point in just a minute. This is simply another statistic showing the ratio or the incidence of individual surface high temperature records by decade in the United States, in the continental United States. This is the decade of the 50s, and the ratio of high temperature records to low temperature records is pretty close to 1. And that remained true through the 80s, but in the 90s it started to creep up. In the first decade of this century, the ratio is over 2, and in 2011 it was 2.7. So this is the shift of this distribution. You're going to see more high temperature records and fewer low temperature records. An important point to make, though, is you still have low temperature records, okay? It's going to be a long time before you don't see low temperature records anymore. Right? It's just a question of the statistics being weighted in one direction or another. There is, unfortunately, in the issue of temperature, an actual upper bound or tolerance of the human body to heat that you can't go beyond. And that's not pertaining to temperature itself, but a quantity called the wet bulb temperature, which is a function of both the temperature and humidity. We have an absolute upper bound of 35 degrees centigrade in wet bulb temperature. If you go outside completely naked and it's 35 degrees centigrade wet bulb temperature, where you will actually die after a while. Your body can't get rid of heat fast enough. If you've been in a sauna, it's like that, and you can stand it for a little while, but you've got to get out after a while. The incidence of the probability of exceeding that is shown in the current climate by this red here. This is the human limit on wet bulb temperature. The actual wet bulb temperature just never gets up to that point. If you had a lot of warming, as shown on the bottom graph, then there are places, particularly in the tropics, where you would exceed that rather commonly. So there is a sort of upper bound. Now, one thing that we are quite confident about, and again, you don't need supercomputer models, you just need to take a course in climate physics and do 3 lines of math and you're there, is that hydrological extremes get more extreme when you warm the climate. That is, places that are already wet get wetter, places that are already dry get drier, and in general, rain is concentrated into fewer but more extreme events. So one expects to see, and in fact one is beginning to see, increased incidence of both floods, blizzards, and drought. Okay? Drought actually becomes a more serious problem. Drought is perhaps one of the big issues we worry about when we ultimately worry about consequences for climate change for us. Severe thunderstorms, which include phenomena like tornadoes and hailstorms. You don't hear much about hailstorms unless you work for an insurance company. Then you hear about almost nothing but. These do an incredible amount of damage around the world. You typically don't kill people. But these phenomena, hailstorms, tornadoes, severe thunderstorms, are all related. And this is a particular kind of phenomenon which my profession does not understand the relationship to climate of this phenomenon. We actually understand the physics of these things quite well. It's a very wonderful story of how we learned about severe thunderstorms. But we haven't worked on how these storms are related to climate. So I can't tell you anything about them, whether they're going to become less frequent or more frequent or not change at all. And I think everybody in my profession would tell you that story. We have to say, we don't know. Someday, I think we will, but we're not there. Insurance companies are very worried about this kind of phenomenon. I mentioned hail and tornadoes, and this graph is, don't have a lot of time to talk about it, but it is essentially the ratio of something called a combined ratio, the ratio of insurance payouts to premiums in the United States as a function of time due to things that aren't earthquakes and aren't hurricanes, and that turns out to mean mostly hailstorms and tornadoes. And the graph starts in 1992 and goes to 2011, and you can see this huge uptick. We don't know why that's there. We don't know whether that's global climate change or something else, but you can understand why the insurance companies are very worried about that and would like to know. But we don't know. Now, I work on hurricanes, and other people do as well, and we have learned something about that. We have a very nice body of theory that tells us in a given climate what an upper bound on hurricane wind speeds can be. We call that potential intensity. In practice, a few hurricanes every year, like Haiyan in the Philippines last fall, make it up to this potential intensity. Most of them don't. This is a map showing the annual maximum potential intensity in meters per second of wind speed around the world, showing basically the places where thermodynamically you can have hurricanes, the deep tropics for the most part. And we know that as you warm the climate, that thermodynamic speed limit goes up, and it goes up appreciably. What we don't really understand is the issue of hurricane frequency. And in fact, most of us believe that global warming will actually reduce that frequency. So far, we don't see any change. This is the global number of tropical cyclones going back to 1980, which is a kind of the first year we think we have an accurate global count of those storms, and you really can't see any trend in that. But my profession doesn't really have a theory that even tells us we should have order 90 storms on the planet a year. The Atlantic is kind of an interesting place. This is a place where we've had good measurements going back quite a few decades. And this is a measure of the power generated by Atlantic hurricanes every year, going back to the end of the 19th century. And you can see that it has a very strong 11-year cycle, which we don't understand and know it's not sunspots. We checked that. They also have an 11-year cycle, but that's not what this is. And then you have this sort of seesaw pattern on a longer time scale. The remarkable thing is if I overlay on this chart the temperature of the tropical Atlantic Ocean in red, you can see a very nice correspondence. All right, so there's a strong relationship, as the thermodynamic theory basically suggests there should be, between the sea surface temperature of the tropical Atlantic during hurricane season and basically the energy of hurricanes. So that's nice, and it might even suggest that we know something about it. But the fact is that the sensitivity of hurricane power to sea surface temperature is way, way, way more than we can justify based on theory. So we know we don't know something, right? The hurricane power has more than doubled since the 1980s, and yet we've only had about a ½ degree centigrade temperature change, and the theory just doesn't predict anything like that sensitivity. So we just don't know, right? We would have predicted some response, but nothing at that, like this magnitude. Now, we try to look ahead, and we have developed a technique at MIT for inferring what hurricane activity might be in the future based on the output of global climate models, which themselves are too coarse, really, to predict hurricanes. And what we do is we take the output of those models and we seed that output with little proto-hurricanes, and then we use very specialized ocean atmospheric models to make estimates of how the hurricane activity responds to global change. So this is an example of about 1,000 hurricane tracks that we generated from this method, not on the output of a climate model, but on the but basically just coarse-grained climatological data of large-scale winds and temperatures, humidities, and so forth in the atmosphere. So we can run these tracks through very powerful statistical tests against nature to see how well they do in reproducing hurricane activity in the present climate, and they do quite well. Here's an example of 50 tracks that are filtered to come within a certain distance of New Haven, Connecticut. There's a particular track, synthetic track, showing the peak winds at every point experienced in the course of that event. The black line is the track of the center of the storm. I'll skip over that. And this algorithm also predicts rainfall from tropical cyclones. And that's one of the big worries we have from climate change, is that every technique we've applied and just plain old basic physics tells you that rainfall should go up rather fast as you, from tropical cyclones, should go up rather fast as you increase the temperature. We couple these hurricane models to storm surge models. Storm surges are usually the most destructive aspect of hurricanes. That's what happened in Sandy, for example, in New York, Katrina in New Orleans. It was a storm surge, by the way, is the same phenomenon as a tsunami hydrodynamically, except it's excited by wind rather than an earthquake, but it behaves the same way. So if you've seen movies of the horrible tsunami in Japan, for example, that's what it's like, except that it occurs in the middle of a hurricane. And that's one of the things that makes it very destructive. So we have some fairly sophisticated hydrodynamic surge models we couple to these hurricanes. And this, by some interesting coincidence, we published a paper estimating surge risk at the Battery, which is the southern tip of Manhattan. This paper came out 6 months before Sandy, all right, suggesting that if you go to a 3-meter surge here, this is return period. So as you go to higher surge levels, of course, they become less frequent, or the return period becomes greater. We would have estimated that a surge of Sandy's character was about a 1 in 700-year event. All right. I'll come back to this in just a minute as I finish up, but if the climate isn't changing, and it may not be changing in a way that affects hurricanes in New York, then we were witness to a very rare event when we saw Sandy. Rare in New York, anyway. But we can apply this downscaling to the output of global climate models, and we have done so for 5 models. And that predicts that globally, actually, one should see an increase in the incidence of hurricanes. This is the projected annual frequency of storms. This is year, so we're about here now. And the width of these boxes shows the sort of scatter among the various different models that we applied this technique to. So there's uncertainty, but some indication of an increase. And we can translate that to what that means for local risk, but I'm going to skip over that for now. So when we run this, and again, this is a paper published before Sandy, but we ran this to estimate surge risk, say 100 years from now in Manhattan, downscaled from 4 different climate models that you see here. So this is flood height versus return period. The black is the current climate. The red and blue are future climates, all of which assume that the background sea level has gone up by about 1 meter, which is sort of the middle of projections by the end of the century, and all of which produce quite an increased risk of surge in New York City. So for example, this model down at Princeton, New Jersey, a surge that might happen every few thousand years in the current climate happens, every 200 years or so in a future climate. So that's a really big increase in surge risk, although the amount of increase varies from one projection to the next. So there's uncertainty there. Well, let me wrap up so that there's time for questions here. The climate is generally warming owing to an increase in greenhouse gas concentrations. That isn't the full story. There are other things going on. There's natural variability. There's response to volcanic eruptions, changing sunlight, and so forth. But the long-term warming trend is mostly ascribed to changing or increasing greenhouse gas concentrations. Much of the tangible risk of the climate change is in changing occurrence of extreme weather events. What we know about that depends very much on the event that you're talking about. And we don't have, unfortunately, a good grasp of how extreme weather in general might respond to climate change. But clearly, heat waves should become more frequent and cold waves less so. The incidence of floods, particularly from storms like hurricanes, increases fairly rapidly. And somewhat ironically, the incidence of drought also increases rapidly. This drought and flood problem is something of major focus in our Department of Defense. If you read their last quadrennial report from 2010, they rank global climate change as one of the top US national security threats. And their main concern is with the effect of climate change on supplies of fresh water and food, agriculture. So they see a lot of potential for political destabilization in parts of the world which are already climatically marginal, like the Middle East. Huge immigration pressures, armed conflict, and the whole thing. It's a kind of a sobering report to read. Very little is known so far about how severe thunderstorms, which produce hail and tornadoes, might respond to climate change. We really just don't know. I hope if I come back here in 10 years, we might be able to say something, but at the moment, we really can't. The frequency of the most intense hurricanes, which in practice dominate hurricane damages, is projected by a number of different methods, including the one I showed you here, to go up. And hurricane-related flooding, both from storm surges and from rainfall, is projected to increase, both because of rising sea level and the increased incidence of very strong storms and enhanced rainfall. So I'll leave you with those thoughts, and I'm happy to take questions.
The oceans cover 67% of the Earth's surface, and oceans are a very good heat reservoir, great thermal inertia, and also absorb CO2 efficiently in sedimentation as calcium carbonate. So to what extent did the oceans retard the effects of global warming? Or what happens to the absorption rate for CO2?
So those are both excellent questions. At the moment, if we tally how much carbon we've actually put in the atmosphere from emissions over time, and we look at how the concentration of CO2 has changed in the atmosphere, which is very well measured, we infer that roughly half of our emissions have actually gone into the ocean. And so about half the carbon that we put into the system ends up in the ocean as dissolved CO2, which ultimately affects, and in fact, it's one of the other things I might have mentioned in my talk, is that lowers the pH of seawater. And this is a major concern to marine biologists because it, at some level, begins to affect the ability of certain organisms to build shells, like corals and other things. And so this is another risk of carbon dioxide that actually hasn't to do directly with climate, but just the mere presence of CO2. So the folks who study the carbon cycle of the ocean believe that there's a limit to how much carbon the ocean actually can absorb, and that to some extent determines the slow decay of carbon dioxide in those projections I showed you where we turn off emissions at some point and go down. The thermal inertia is another issue, but most of the heat goes into the upper ocean, it turns out. So at least on the 100-year time scale, you're talking about a few years, but not a long time. Yeah, not from the thermal part.
Bruce? Me? Yeah. So it seems unlikely that the countries of the world are going to suddenly play nice and cut back on CO2 emissions. Is there any? I'm an engineer. Don't laugh too hard at my question. Is there any way? Are people thinking about kind of sucking this stuff back in?
Yeah, that's a really good question too. Yes. And the short answer to your question is absolutely. There's a whole bunch of research going on, in my personal view, not nearly enough, on carbon capture and sequestration. And the last conference I went to, which is now actually about a year ago on this, where they looked at the economics of doing this, said that if we started to do that today with today's technology, we actually started doing it, and we passed a carbon tax or something to fund it, that the net effect would be to double the price of energy. And to an economist, a factor of 2 sounds like an apocalypse. To a scientist or an engineer, it sounds very doable, right? It wouldn't take much, perhaps, to beat that factor of 2 down a lot. So I personally think there's a lot of hope for this. But right now, the United States is not investing a lot in R&D on carbon capture. Canada is, at least per capita basis, investing a lot more, for example, in Europe. But there are other techniques which are much riskier in climate sense, like what we call solar radiation management, which in fact means, in practice, injecting a lot of sulfates into the stratosphere to reflect sunlight. We can do that. Technically, we can do that today. And it's not very expensive to do it. So cheap that a small country or even a wealthy individual could do it unilaterally, which is kind of a worry. The problem is there are all kinds of side effects from that, and we would not pretend to understand that fully, those side effects. So that's their risk. But that whole geoengineering field is a very interesting and rich subject. You should get somebody in here to talk about that, but much more than I have time to talk about at the moment.
We have a webinar.
What is the single best source of updates on the science of climate change forecasting for people doing outreach to the general public but not able to attend academic conferences?
Well, that's there's a certain subjectiveness to my answer to that very interesting question. Of course, as Bob pointed out, I've actually written a book that tries to do that. But shy of that, I would have to say that the IPCC report, which is freely available online, and where you can do nothing more than read the summary if you want to get kind of each chapter to get an overview, or drill down to get a good encapsulation, it's really very good. I mean, it may not be the best prose in the world because it's put together by huge committees, but the IPCC is not a research organization. It's just a communications effort. It's a bunch of scientists getting together to survey the field and put out there for educated non-specialists what we know about climate change. So I would recommend that. It does have the big advantage also of being free. Right.
Another webinar?
How does this relate to the current weather conditions the U.S. is experiencing and ice cover of the Great Lakes, which is the most over the last 100 years?
So how does this relate to the fact that it's been so cold around here recently? Well, Tip O'Neill is famous around here for having said that all politics is local, and my analogy is that all climate is local. No matter how much you talk about global climate, what people actually experience in their own neighborhood or their general vicinity really influences their feelings about the subject. So much so that professional pollsters has noted a very strong correlation between belief among the general public in global warming and the temperature of the room in which the poll was conducted. I'm serious. I mean, it makes a difference. I think Jim Hansen cleverly turned up the heat in the particular room that he testified in 1988 before it's already summer, so that wasn't so nice. But there will always be weather, and there will always be El Nino, and there will always be short-term climate variations. And you really have to be careful to distinguish the signal from the noise. And to see a signal in global climate change, you really have to look over long periods of time and large areas for the most part. Small fluctuations. We're going to set cold temperature records for the foreseeable future, just not at the rate that we set high temperature records.
Okay. So that end of the century temperature change distribution graphic you showed based on those Cambridge model ones, is that work published any place?
Yes, it is.
It
yeah.
is.
Please send me an email. I don't have it right at the top of my head where that appeared, but I'll send you a link to it. Yeah, sure.
I'm sort of wondering, given the pictures of the different distributions that you showed, right, where you have one where the mean shifts and one where the variability shifts and then one where you have both. From a planning perspective, if you're looking at shorter planning horizons than say 40 or 50 years for something, maybe the longer term recurrence events like Sandy are less important than some of the shifting that you see for the means, like an earlier thaw or something in the mountains leads to increased storm runoff and things like that. So, I mean, sort of what is the state of the science with regard to that sort of more seasonal, maybe is a better word for it, sort of level of planning that would influence some of our clients' decisions?
So I think the importance of your question is that at the end of the day, what you need to know about climate change, right, depends very much on what you're doing with it. So you mentioned, for example, the length of growing seasons. It's very important, and that's not a matter of extreme events. It's just a matter of a shifting distribution. The problem is that, when I said all climate change is local, I sort of mean it. It really depends upon what's happening locally, let's say in a growing season in the central U.S. plains. And we're much less confident about predicting changes when you go down in scale in space or down in scale in time, like the near term versus 100 years from now is much harder. And just talking about the central U.S. is much harder for us than talking about the globe. Models disagree, for example, what happens regionally. So unfortunately, you have to trade off precision for accuracy when you go down to these scales, and that's tough because you still need to do something. You need to account for the risk.
what recommendations would you make to the MBTA, Massport, or the Mass Highway Department to plan for our new climate?
Well, I'm probably not exactly the right person to ask that question, but when you look at transportation systems, people in this room are far better qualified than I to talk about that, but extreme events are important. Big snowfalls, flooding events. I worry, because I'm at MIT, that MIT hasn't thought very carefully about its flood risk. The Charles River emptying into the harbor, you get a meter of sea level rise and a mild storm surge, and at the same time you have a very heavy rainfall. That's MIT would be in trouble. Yeah, and Volpe, and maybe the subways as well. So I wish I could offer a better answer to that question. And what I can do, I think, is to inform people who understand the transportation infrastructure a lot better than I do about what kinds of risks you might be looking at in a particular region.
Did anyone factor in solar variability, like the Maunder minimum, little ice ages, or the next glaciation? I mean, we are in pre-glacial right now.
That's right.
How do you fold that in?
Well, there are ways to do that. In the case of the great glacial cycles of the last 3 million years, of which there have been approximately 10, we actually have made a lot of progress. We know what caused them. Without much doubt at all, they're caused by very periodic variations in the Earth's rotation axis and in the orbit of the Earth around the sun. And those are highly predictable. Right, but we're now talking about climate change on a 10,000-year scale. So on the 10,000-year scale, we're headed into another ice age, right? But, the immediate problem is the next 100 years. It's a completely different time scale. So we're not going to go into an ice age in 100 years for sure. It's a 10,000-year problem.
100 actually.
Sorry?
For little ice ages.
Yeah, but that's a different climate phenomenon, even though it's called the Little Ice Age. There's a lot of argument about whether that was local to Europe or whether it was truly global. The evidence is kind of equivocal about that. There was a very strong minimum in solar magnetic activity called the Maunder minimum. You mentioned that. During that time, it's not clear whether that was a coincidence or whether that had something to do, but very few climate scientists doubt that solar variability has something to do with climate. And one thing you have to do is not fall into the trap of thinking that climate change is caused by A or B or C. It's usually all of the above.
All right. Well, very good. Thanks again.
Thanks. Yeah, appreciate it.
Very informative, and there have been some questions about what does this mean for transportation, and we're going to start talking about that with our next speaker on Tuesday, March 11th, where Bill Lyons, who's a principal technical advisor here at Volpe, is going to talk about the challenge of transportation planning for resilience. So we look forward to seeing you there and having those of you on the webinar link in. We also have a speaker this Friday, Dr. Lisa Altman Hall, who's director of the University Transportation Center at the University of Vermont, will speak on transportation livability. What's that really mean for rural transportation systems? So you can keep up to date on all of our speakers on our website. We look forward to your participation in the future, and thanks again to Dr. Emanuel.